The sampling distribution of a sample proportion. What in the heck are we trying to say here? Okay. Well, remember that we're talking now about proportions. Proportions are relate to categorical data. Okay. Do you drive to school? Yes or no? What's your favorite color? You can't answer six, right? You fit into one of several categories. So we're going to look at categorical data right now, categorical variables. The sampling distribution of the sample proportion p hat describes the distribution of the values taken by the sample proportion p hat in all possible samples of the same size from the same population. So say we know the answer to the population. We know that 37% of the Americans watch Survivor. If I took samples of size whatever, the last example we looked at sample sizes of n equals 100 and n equals 1,000. The sample size really doesn't matter in describing the center of the sampling distribution. Regardless, you saw when n equals 100, we hit the target. The sample mean of all those p hats was equal to the true answer of p. And we took a sample of size n equals 1,000. Well, guess what? The center, again, hit the true population proportion p of 37%. So regardless of sample size, the center would not be affected. Okay? So this seems kind of intuitive, like, yeah, duh, it makes sense. But this is super important idea. If I take the mean of every single possible p hat that I can, guess what that means is going to be? P. If I took every single sample and then I averaged all those samples, well, yeah, I'm going to get the true answer of the entire population. So describing a sampling distribution, shape, center, spread. Well, we'll see later that the shape is going to be normal as long as n is large enough. It's going to give us that nice symmetrical bell-shaped curve. The center, if we're looking at categorical data, so the mean of all the p hats is equal to p. Excuse me. However, the standard deviation, which is the spread we saw in the last bar graphs or dot plots, histograms, whatever graphs we were looking at previously for the survivor data, we saw that the spread changed as the sample size got larger and larger. So you can see this formula for the standard deviation of p hat. The standard deviation of p hat is equal to the square root of p times 1 minus p over n. So this is what's making that spread smaller. As n gets larger, the spread gets smaller. Okay? And it looks like somebody shot up our diagram here, all these things that were in the book. Just anytime you come across anything that looks weird like this, just look at the white. When they have two things written next to each other, as you can tell up here, this red, the computer printed it out wrong. So just look at what's in the white, the p hat. Okay. Now, this formula for the spread or the standard deviation of the sample proportion p hat only works if this condition is satisfied. So as long as the population is at least 10 times the size of the sample. We saw this rule in the previous chapter 6. When we were looking at binomial distributions, we saw this. This formula for the standard deviation of p hat only works if the population is at least 10 times the size of the sample. So if we look back at the survivor problem, we had samples first of size n equals 100. Well, what do we mean the population is 10 times the size of the sample? Well, if we're looking at the entire population of the United States, there are certainly more than 10 times 100 people in the United States. Okay, there's certainly more than 1,000 people in the United States. So the population is at least 10 times the size of the sample. That's what this is trying to say. If we look at size n equals 1,000, well, we'd have to make sure that there are more than 10,000 people living in the United States. We're safe there. Therefore, this formula for standard deviation could be used for that survivor problem. But as you can see, when we divide by n, as n gets bigger and bigger, the spread or the standard deviation is going to get smaller and smaller. Okay? Now, we talked about, wow, they both look normal, regardless of size, n equals 100 or n equals 1,000. Will it always be normal? Will the sampling distribution always give us that nice bell-shaped curve so that we can use z-scores? Well, not always. But as long as n is large enough, it will. Well, how large is large enough? How big of a sample size do we need to make sure that we get a normal distribution? And that's what this final rule is showing us here. As long as n times p and n times 1 minus p are both greater than or equal to 10, then the data is approximately normal. Well, we saw the same rule in binomial. It said, oh, when can I turn binomial into normal? Well, when n times p and n times 1 minus p are both greater than or equal to 10, a binomial distribution becomes approximately normal. Well, when will a sampling distribution become normal? Same rule as when binomial comes normal. N times p and n times 1 minus p are both greater than or equal to 10, we're good. We can assume normality. That's going to be very important for us as we move forward. All right, so check out some examples here. The approximate sampling distributions of p hat. Okay, the sample proportion of orange candies for different combinations of p. Okay, so let's kind of look at these slowly as we move through. This first graph up here on the top left. P hat is the sample proportion of orange candies from a population where there are 10% of the candies were orange. Okay. If 10% of the candies are orange and we took samples of size n equals 25, does this look normal? Nope, not really. Doesn't really look normal. Why do you think that happened? Why was this distribution not normal? Well, we said that the sample proportion would be approximately normal if n times p and n times 1 minus p were both greater than or equal to 10. So 25 times 0.1, n times p. Well, 25 times 0.1 equals 2.5. That is not greater than or equal to 10. That's why we cannot guarantee that this distribution is going to be approximately normal, because it didn't meet that rule. Okay. Now, down bottom, p was equal to 10 once again. Same proportion of orange candies. 10% of all the candies in the bag were orange. If we took an SRS of size n equals 100 now, look at this distribution, does appear to be normal. Why is this one down bottom approximately normal when the one above is not? Well, because the one down bottom meets the rule. We used to talk about these as rule of thumb back in the old days. Now they just say, know this rule. Okay. 0.1 times 100, that equals 10. 0.9 times 100, that equals 90. Both of these are greater than or equal to 10. Therefore, it assures us that the distribution will be approximately normal. Okay? Now, if we look at the next set of examples here, still we're looking at the proportion of orange candies. Now in the bag, half of the candies are orange. Okay? So we would expect the center of this distribution to be 0.5 because p equals 0.5. We said the sample size doesn't matter for the center. The center is always going to be the center. Okay? So yeah, 0.5 is the true population proportion. We know that half of all the candies in this population are orange. 0.5, right in here. Yeah, that's the center of the distribution. So the sampling distribution, p hat, the mean equals p. Remember we said in the last slide that the mean of p hat is equal to p. Yep, we hit the mean. The spread looks like it goes maybe out here from like 14, 15, all the way out here to about 80. Pretty big spread. Now, does it appear to be approximately normal? It does look normal. Why did that work? Because n times p, in this case, n was 25, times p, 0.5, and n times 1 minus p, in this case, 1 minus p is also 0.5. Both of those are equal to 12.5, which is greater than 10. Therefore, we know the data is going to be approximately normal. So shape, symmetrical, approximately normal. Center, 0.5, because the mean of p hat is always equal to p. Now, down bottom, same population, where 50% of all of our candies were orange. Well, where's the center? Well, guess what? It's at 50%. No surprise there. The mean of p hat equals p. Okay? It is symmetrical and normal. You bet it is, because n, 100, times p, 0.5 gives us 50, which is certainly greater than or equal to 10. Okay? What's different about these two graphs here? The spread. Why is the spread so much smaller when n equals 100? Because to find the spread, and remember the standard deviation of p hat is equal to the square root of p times 1 minus p over n. Well, as n gets bigger, the spread gets smaller, and you can see that it's true here. And then finally, in this last set of graphs, now we have a population in which 90% of all the candies are orange. Where do you think the center is going to be? You bet that center is going to be at 0.9. And if you looked at this and you found the center, yep, somewhere right in here at 0.9. Where's the center here? Yep, somewhere right in there around 0.9. That should not be a surprise to us at this point. Now, excuse me, the one at the top does not look perfectly normal. In fact, it looks slightly left skewed. Why is it skewed? Well, let's check the rule. We know it'll be normal if n times p and n times 1 minus p are both greater than or equal to 10. Well, in this case, n, 25, times the proportion of success, 0.9, and n, 25, times 1 minus 0.9, both have to be greater than or equal to 10. Well, 25 times 0.9 is 22.5. Greater than 10, we're okay. But remember, the rule says and, meaning they both must be. So 25 times 0.1 is 2.5. 2.5 is not greater than 10. Therefore, the distribution's not going to be normal because it didn't meet the rule of thumb that n times p and n times 1 minus p both must be greater than or equal to 1. So what are we trying to see here? That the center is going to be the center regardless of the sample size. Now, sure, we could get sample that's too small and there might be some exceptions, but in general, the mean of p hat equals p. If I take enough samples, I'm going to start to find where the center is. And if I average all the p hats I took, it's going to give me the true population proportion p. What happens to my spread? Well, as n gets bigger, my spread gets smaller. How do I know if it's going to be normal? Does it meet the rule n times p and n times 1 minus p, both greater than or equal to 10? All right, so sampling distribution seems pretty easy. The formulas aren't crazy. There's not a whole bunch of calculations, but conceptually, super important for us that we understand what's happening here. Okay, so let's look at an example. A polling organization asked an SRS of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of their home. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value. So, what do we know here? It's kind of like doing a puzzle. Let's turn over the pieces first. Before we start building the puzzle and putting the picture together, we need to see what the pieces look like. So we're given what? N equals 1,500. Okay? And we know that P, the true population's parameter, is 0.35. We know that 35% of all college students go to school within 50 miles of their home. Okay? And we want to find the probability that the random sample of 1,500 students will give a result within 2 percentage points. So we want to find out what is the probability that p hat is within 2 percentage points. So the probability that p hat is plus or minus 2%. Well, I'm not sure how to go about solving that problem. So really, what am I trying to do? I know I want to find the probability that p hat is within 2 percentage points of p. So I'm trying to find the probability that p hat is between 0.35 minus 0.02. It's greater than that, but less than 0.35 plus 0.02. So really, I'm trying to answer this question. What's the probability that I take a sample of size 1,500 and my sample proportion, p hat, is between 0.33 and 0.37? Well, I know that it's normal. How do I know that it's approximately normal? Well, because n times p, 1,500 times 0.35, and n times 1 minus p, both must be greater than or equal to 10. Yeah, they're both way bigger than 10. So I know it's going to be normal. Where's the center? Well, I know that the mean of p hat equals p. So the center is 0.35. What is the spread? I'm not sure what the spread is, but I have a formula for it. Okay. I'm allowed to use this formula that the standard deviation of p hat is equal to the square root of p times 1 minus p over n, if and only if the population is at least 10 times the size of the sample. Sorry, I got the hiccups. So the sample size is 1,500. What's the population? All college students. So I have to ask myself, are there more than 1,500 times 10 college students? Are there more than 15,000 college students? Well, yeah, absolutely there are. Therefore, I am allowed to use this formula to find the standard deviation. Okay? So I need to just plug and chug now. I'm going to take the numbers and put them in, do the work. 0.35 times 1 minus 0.35 divided by 1,500, and square root that to get the standard deviation. And I'll find that the standard deviation is 0.0123. I'm not going to show you how to punch that into the calculator because I trust you guys can push buttons. So the standard deviation is 0.0123. Now I'm supposed to find the probability that I find a sample of size 1,500 which lies between 0.33 and 0.37. Well, let's get our muscle out here so he can do the heavy lifting for us. If you recall back to normal calculations, where did we find those at? Well, any kind of distribution lives in second vars. Remember, we never use normal PDF. We will only use normal CDF. What do I want my lower bound to be? Oh, my lower bound is right here. My lower bound is 0.33 because that was the question I was trying to answer. So 0.33. My upper bound, I'd like to go all the way here to 0.37. 0.37. Okay. What's the mean of this distribution? Remember, the mean of p hat equals p. So the mean is 0.35. And then what's the standard deviation? Well, I just calculated the standard deviation. It's 0.0123. Then I'm going to let the calculator do all the work for me. Paste it in. Again, if you don't have a TI-84, you'll have to get normal CDF, parentheses, lower bound, upper bound, mean, standard deviation. And then hit enter, and it says, oh, approximately 90% of all my samples of size 1,500 will be within 2 percentage points of the true population parameter, 0.35. So again, the calculation's simple. We did this way back in chapter 2. Nothing new there. Okay. Why is it normal? Are we allowed to use the standard deviation formula? That's what's new. Okay. How do we know that this is okay? All right, so the big ideas that we need to remember here is that the mean of p hat is equal to p. Always, the mean of p hat equals p. The standard deviation of p hat is equal to the square root of p times 1 minus p over n, if and only if the population is at least 10 times the size of the sample. The data is normal. Well, does n times p and n times 1 minus p, are they both greater than or equal to 10? Yep, therefore it's normal. So again, it's just z-scores, but now we have to check a few rules to make sure that z-scores will apply.